Now, do you want to see Vasicek in action in the absence of randomness? We will solve the full equation on Thursday, but just because we did that for a stock, let's do the same for an interest rate. So let's come back here. Let's write down Vasicek in the absence of randomness. Right, so let's write that down. dr is minus gamma r minus r bar dt. Okay, everyone happy with that? So again, another first order differential equation, agreed? Now, let's write this down as dr over r minus r bar is equal to minus gamma dt. Let's integrate. If we integrate this, we get log r minus r bar is minus gamma t plus a constant c. Let's rearrange this, take exponentials of both sides. So r is equal to r bar plus a e to the minus gamma t. And that's what the solution of that is in the absence of randomness. Now, when you see, so the important thing here is this. When you see that, what does that remind you of? Exponential decay, right? The larger gamma is, the quicker this is going to vanish to zero. And the smaller it is, the longer it will take to decay. So what's happening is, as this decays, the r is tending to r bar. But obviously, it won't tend to r bar really because we've got the random term. But this is telling us what the role of the gamma is. So in other words, when gamma is small versus large, let's have a look at what happens. So this is what we have. Gamma high, gamma large, and gamma small. When gamma is large, it's tending to r bar like this, assuming that the interest rate is above r bar at time t is equal to 0. And when it's coming up from beneath r bar, it's going to do this. On the other hand, when gamma is small, it's going to be enjoying life in the slow lane like that. So you can quite clearly see what the effect of the speed of reversion is. So it's, whether we call it the speed of reversion or just the speed, we're talking about exactly the same thing. How long does it take in years to revert back to the mean? And again, just solving Vasicek by switching the randomness off has given us quite a lot of information about the solution. Now, what else does it say? It says, when you get to the fixed income modeling module, you'll do a lot more on this, and you'll do bond pricing in terms of stochastic interest rates. So rather than assume that the interest rate is fixed, the interest rate will be a random variable. Now you might be thinking, but in bond pricing, we lock in at today's price. But what would happen if you actually wanted to sell your bond? How would you know what the price of the bond is like prior to maturity? So that will depend on what the interest rate is at that time. So therefore, if you want to do serious bond pricing, you assume that your interest rates are stochastic. Okay? Now, pursuing this idea further, imagine what might be meant by this. This is actually a much smaller version of what we've been doing. We've been assuming that this is dependent on both W and T. Right? Remember we said that, so in this particular case, what Paul is saying is consider a stochastic process, and you want to look at how it evolves in time, then you would write it down like this. And if you can write down like this, then W is called a diffusion process. So whether we say that this is a stochastic differential equation for W or a random walk for dW, we're talking about exactly the same thing. Two different names for the same kind of behavior. So an SDE, stochastic differential equation for W, or a random walk for dW. Their precise meaning comes out from the technically more accurate equivalent of a stochastic integral. Now, we've already looked at a stochastic integral. We looked at the Ito integral, didn't we? We can write down a stochastic differential equation in two forms. You've already seen the differential form. So let's come back here. So here's an SDE. SDE for, let's say, G. dg is equal to some function, so shall we say a of gt in t dt plus b gt t dx. There we go. There's a stochastic differential equation. That is differential form, agreed? Because it's d of something. If I now integrate, let's integrate both sides. Integrate both sides over, shall we do 0 and t? So 0 and t dg, dummy variable, so I'm using it less there, is equal to this integral gs s ds plus integral b gs s dxs between 0 and t. Now the left hand side is nice because you've got a differential. So that differential and that antiderivative will cancel each other out. So we get g evaluated at t minus g evaluated at 0, which is some kind of initial condition. So we can write this down as g of t minus g0, which I'll take to the other side, plus this. Okay? This is the same as the very first line, so let's make that quite clear. I'll call this star, and I'll call this, there's not enough space there, is there? There's GT, I'll call this dagger. Star and dagger are exactly the same thing. They're both different ways of writing down a stochastic differential equation. So the very first one is a differential form, and then the last line, this is an integral form. But we should appreciate that anyway, because we know that a differential equation can be written down in terms of integrals anyway when we solve them. Okay, so two ways of writing down an SDE. And you can go back from here to there by simply taking the G naught on the other side. Now, the last term here is very, very important. We come across the Ito integral again. Okay, so this term here, this is the Ito integral. And for that reason, we spend a lot of time looking at Ito integrals. This whole subject is sometimes called Ito calculus for that reason. So let's see how far we got. All right, so Paul, that's what Paul is basically saying here. That is the same as this, but if you look at this, he's obviously assuming that W0 is 0. Otherwise, there'd be an extra term there. Okay. Now, the last bit, I will give you detailed notes on this, but this is an important property, and it also ties up with this idea that dx squared behaves like dt. And whether we call it the mean square limit or mean square convergence, we're talking about exactly the same thing. So Paul says to examine this particular expectation. But before we do that, let me just say something. Now, mean square limit. Let's consider a function. Some function, right, f of x, it comes back, and we minus some quantity L. We square it, and we take the expected value of this. If this tends to 0, we say that f of x, oops, that's a capital X, isn't it, not small. We say f of x tends to L in the mean square limit. Right, so it's important that you understand this first. All right, so you've got a difference between f and its proposed limit. You square it and then you take the expected value. If that tends to 0, then we say that f of x tends to L in the mean square limit or the mean square sense. So it's important that this is taken on board before we look at what Paul's saying on this in the slides. Now, the version that you will get typed up has many pages because it goes through absolutely every single line of working and also suggests another way of obtaining this. So here's this quantity. Examine that quantity, right? Because what's going to happen is later on you'll see that that tends to 0. And at this point, what I'm going to do is this nasty looking thing here, I'm going to call it something else. So this is still Brownian motion. I'm going to call this thing here that's being squared. I'm going to call that ytj. So what we end up looking at, because that will actually simplify things greatly, sum j equals 1 to n of ytj minus t, we square that and we check to see whether that tends to 0. And the reason I'm going to go through a bit of this now is because one of the things we often get asked is where the extra term comes from later on. So if you now, first of all, if you actually open up what's inside these square brackets, it's this minus t squared, so that times itself. So shall we go here? Let's just go here for a second. So what we have is, inside the bracket, we've got y1 plus y2 all the way up to yn. So y1 essentially is yt1, y2 is yt2, but if I put those in, it'll make the working very lengthy. So yn minus t, we square it. Yn minus t. So when you square all of this, you're going to end up with 4 types of terms. So that's something that you can try in the meantime. And if you now go back to the slides, what Paul's done here simply, he's left everything as it is, but what I've done is the reason for bringing in the y terms is because it gets rid of all of these things here, right? So you've got 4 types of terms here. You've got 1, 2, 3, and this term here 4. Okay, and then you start looking at the statistical properties of each of these increments, i.e., you look at the variance, right, which is t over n. Then you look at the kurtosis. Right, so that should all make sense to you at this point. And then you start taking limits. And what you end up with is this. Everything cancels out except terms which are order 1 over n. And then as the partitions become smaller and smaller, this whole thing will become 0. Okay? So you do need to see all the extra bits of working which you'll see later on. But again, this is essentially another justification for writing this down. Which is sometimes also referred to as mean square convergence. Okay, so all that really remains for me to do now is just to remind ourselves of what we did. The starting point essentially was constructing a model for Brownian motion, which we did using a simple symmetric random walk by tossing a coin. We then, after we did that, we looked at the rules of differentiation, and we realized that the normal rules of differentiation no longer apply, and we had to resort to stochastic differential equations, which led to Ito's lemma. We did 2 forms of Ito. On Thursday, we'll do many more forms of Ito. So these were the 2 basic ones. And then we came up with a stochastic integration formula, which had the advantage that it was consistent with Ito because of the fact that we used Ito's lemma to derive it. And then we finished off essentially by looking at some well-known stochastic differential equations. Now, don't forget to bring your laptop on Thursday, because after we've done some maths, we'll also be looking at the mathematics of random number generation in Excel, and then we'll use those to do our simulations. So thank you. I'll see you on Thursday.